Okay, so today we want to show the asymptotic freeness of unitary random matrices, high unitary random matrices from deterministic matrices. And the idea is, we want to replace the Gaussians by the unitaries. And for the Gaussian random matrices, we saw if I multiply if I conjugate a matrix by Gaussian random matrices, I can make them free from other matrices. The only problem is if I conjugate something by a Gaussian random matrix, I'm changing the distribution. So the idea is, if I can use, instead of Gaussian random matrices, unitary random matrices for making things free by conjugating with unitary random matrices, then this is very good because conjugation by unitary random matrix does not change the distribution of my matrix. Because the distribution is given by taking traces of powers, and this does not change while conjugating. Okay, so that's the idea. If we can achieve this, then we really can model any free situation with random matrices. Good, but for this we have to more or less try to imitate what we did for the Gaussian random matrices, to calculate products in unitary random matrices and deterministic matrices. And of course this is getting a bit more complicated because we have to use information about the joint distribution of the entries of our unitary random matrices, and this is more complicated than for Gaussian ones. In particular, the entries of the unitary matrix, and we are using high unitary matrices, the entries are not independent. Okay, so. But we have enough information, and I will now tell you what it is. Good, but maybe let me first record by saying unitary random matrices, I mean high unitary random matrices, and this means I'm looking on a compact group of unitary n by n matrices, and I equip this with a Haar probability measure, which is a measure which is invariant under translations in the group. So this, if I normalize this to be a probability measure, this is unique, and so my random matrix is uniquely determined. Okay, and so what I need to know is the joint distribution of the entries, and the main information about this is contained in something which we call the Weingarten function. So namely specific joint distributions contain the main information. And this I denoted by WGN, alpha. So this is something which of course depends on n, we are looking on n by n matrices, and then it also depends on the permutation, alpha. So alpha is a permutation in the symmetric group Sm, and this is by definition the expectation of a product of entries of my unitary random matrix. Okay, like I'm taking entries and the complex conjugates, and the main information is given if I'm multiplying the same number of them. So let's say I multiply m of them, so this alpha is then this m. So I have this for this I also need that n is larger than m. Also I have this for each m. Also I have here the u11, u22 up to u So I'm multiplying the first m guys on the diagonal of my u, and then I'm multiplying this with also m many u bars, but now not on the diagonal, but on positions which are given by alpha. So the first index is again 1 up to m, but the second index is given by a permutation of 1 up to m. So I have here u bar 1, alpha 1, u bar of 2, alpha 2 and so on, u bar of m, alpha m. Okay, so u, of course, u, my matrix, my high unitary random matrix, is given by the entries ui j. J is running from 1 up to capital A. Good. Okay, and so this object we call the Weingarten function. Because Weingarten considered things like this 50 years ago. Okay, and now the point is that this object contains all information about all moments. If you know this, we can calculate all the other distribution of the entries. Like the Wick formula. If you know the second moment, we can calculate the other ones. Here we need something more complicated, but this is enough. This is only very specific. These are only a few specific moments of my entries of the matrix. Okay, so there is a weak type formula, and then of course we also need to know how this behaves in M. What is the leading order in M? Okay, that's the two things which I will tell you now. I'm not going to prove it, but those are basic facts which we have to know, which are not so easy to prove, but I mean in principle we could do it, but I don't want to spend time on this. So the two facts which we will need about this is first that we have a kind of a big type formula. Which says that we can actually now calculate any moment, joint moment in the entries and the conjugate of the entries of my unitary random matrix. So this means so if I have now a high unitary random matrix, as before, the entries are denoted by uij. So this u should be a hard unitary random matrix. Okay, and then I'm looking on the product of all such guys, and this means I'm just allowing arbitrary indices at all positions. So I multiply m, let's say m of the u's, and m prime of the u bars, and all of them have arbitrary indices. So I need quite a bit of indices. So then we have for all. Okay, now I'm the indices of the u's. I'm denoting by I and j, the first one by I, the second by j, and the indices of the u bar I denote by I prime and j prime. I'll just get some systematic, which will be important later. It's good. I mean, the point of all those things is to write things in a nice form. There are many indices, and it's good to give them a good name so that things fit together here. Okay. So I need here indices. Indices I mean. Some of them I call I. They're running from 1 up to m. And I have those which I call I prime. Also running from 1 to m. And then I have j's. J from 1 up to m. And I also have j primes. Up to j prime. And all of them are between 1 and capital M. So possibly this is which I can have here. Good. Okay, and then my statement is, then we have for all such guys, we are looking now on expectation for the product of m u's. Okay, and actually, let me see. I mean, I'm taking m of the u's and m prime of the u bars. So the guys which number the u bars should also run up to m prime. Also here m and m prime are natural numbers. Okay, so now I multiply m of the u's, and the indices I give to them is I1, j1 up to u I1, jm. Okay, so that's arbitrary indices here. The first index I call I, the second I call j. And then I multiply with m bar of the u, m prime of the u bars, where I call the indices I prime and j prime. So I have here u bar of I prime 1, j prime 1, up to u bar I prime. And now I have here m prime many vectors. Also those guys are running up to m prime, j prime. Okay, and so this is the general moment in u and u bar. So I'm running over all possibilities for m and m prime and over all possibilities for all indices appearing here. Of course, I mean the u's and all the entries commute. So I mean I can always bring it in the form first the u's and then the u bars. Good. Okay, now the point is that I have a nice formula which expresses this in terms of the Weingarten function. So namely, what do I get here? First of all, just by symmetry considerations, the m must be the same as m prime. Otherwise, this guy is 0. So I must have the same number of frequent u bars. So I have delta m prime. And then I'm summing over something. This is like a big formula, summing over pairings. But here actually I'm summing now over permutations. And actually I'm summing over permutations, over two of them. So one is essentially for the first index and one is for the second index. So that's it. So I'm summing over alpha and beta in Sm. Now here is the same as m prime. And then again I have some consistency condition that the indices here must fit together. So this means an index which appears here, an I index, must match. So the first index at a u must match with the first index at a u bar at some position. Okay. And this matching is given by the alpha. And in the same way, the second index of the u must match with the second index of the u bar. So this means I have some connections between the I and the I primes and the j and j primes. So I can match them in different ways. Okay, for each matching I get a contribution, but this contribution is then given by the Weingarten function. So I have here this matching condition, and so this is yeah. You see. Maybe it's better to continue. It's a nice formula, but it's not a formula which fits into this space. It needs a bit more. Okay, now so I continue here. Said I have a sum over alpha and beta in the symmetric group of elements, and then I have delta conditions, which tell me that the sum of the indices must be the same. Or if I'm fixing alpha and beta tell me that some of them must be the same. Maybe I have here delta that I of B1 must be the same as I prime of B. So this means the first index of the I prime, this must match with some of the first indices on this side. So it must be one of the I at some position. This position is beta of 1. And then so on, delta of I of beta m must be the same as I prime of m. So again, also this tells me that the I prime must coincide with the I indices, but at some permuted positions. Beta tells me which positions. So then that's what beta tells me here. And then alpha does the same, but for the second index. So I also like this, and I also multiply it with delta of j of alpha 1 times j prime. So the first index j prime must be a j index at some other position, and this position is given by alpha. The same for all the j primes. So I have the delta of j alpha of m. This must be the same as j prime of m. Okay, so this tells me that somehow the I indices must match somehow the I prime indices. The j indices must match somehow the j prime indices. And this matching is then given by alpha and beta. And if this is the case, then this I get a contribution which is now given in terms of the Weingarten function. So it's not just 0 or 1, but it's a more complicated contribution. But it's given by the Weingarten function, of course at n. And then here I need a permutation, and the permutation which I have here is the product, the inverse of alpha and beta. Okay. So that's the kind of ring formula. So you see, we have an analog of this, but it's getting more complicated. And maybe draw a picture, just get an idea. So let's say I have here I'm multiplying, let's say m and m prime are equal to 3. Then I have here my indices of the u's. So are the pairs of indices of the U's, and then I have the indices of the U bars. So this is the same as primes. J prime of 2, I prime of 3, J prime of 3. Okay, and now I mean I have to match them. So I mean I have to see that, okay, let's see, we start from somewhere. Let's say this I prime here, this must match one of the i's here. So let's say that this here is the same as this I. Okay. I mean then this is the effect of beta. I mean beta tells me, beta of 1 tells me which I is the same as this. Okay, and then of course I mean then I can look on the corresponding J index here, and this must match with the J prime index. And I mean, alpha tells me how this matching works. So this guy, for example, let's say, matches this one. Okay. And I mean, the effect here is actually going this direction, alpha to the minus 1. So going in this direction is beta, going here is alpha to the minus 1. Okay, and then I can look again. Okay, so this is matched with this, and now I can look on the I prime index here, and this must again be matched with some index here. Of course, it cannot be matched with this, because this already is the same as this. So this, let's say, let's say what? I2. Yeah, so let's say this I2, for example, is matched with this guy. Okay, then the J here must again match with some of the J primes, so the J3, and let's say this is matched with this one. Okay, and now you see actually I have somehow I have matched all those guys, and what I have here is essentially a cycle of alpha to the minus 1 beta. Okay, so I mean the cycles of alpha to the minus 1 beta tell me the subsets of indices which are already matched. Okay, and then of course I mean I have more. I have matching. Of course now this guy here must also be matched with something, but of course there is only one thing left. This has to be matched with this, and then of course this has to be matched with this. Okay, and so I mean alpha to the minus 1 beta here decomposes essentially into two cycles. It tells me that those guys here belong together, and that this here also is this one. I mean alpha to the minus 1 beta gives a matching between, if I go alpha to the minus 1 and then beta, then going back, this gives a matching between what? Between the J and the I indices here. Okay, but anyhow, also, so I mean, you see here that the cycles of alpha to the minus 1 beta really correspond to the effect that I'm decomposing these indices here in subclasses which are somehow connected to this. So if it's somehow it's meaningful that alpha to the minus 1 beta shows up there. Good, but anyhow, also that's the general formula. And then, yeah, for each such matching, we have a contribution which is given by the Weingarten. Okay, and then of course the second thing which we have to understand is what is the asymptotics of the Weingarten function. And this is also something which I want to tell you, which you have to use. So this is the asymptotics of the Weingarten function. So I have to say what is the argument of the Weingarten function is alpha. So what is for alpha and Sm? So what do we have? So the Weingarten function of n and alpha. This has some asymptotic behavior in n, so it goes with some power in n. And the highest power is again something which you can write down in terms somehow of the cycles of alpha. Okay. And of course, I mean there's a coefficient. So I mean the leading coefficient will not be 1. It will be something which I now call just phi of alpha. I'm not really telling you what this is. Actually, it's not important what this is for our purposes. What is important is the power here of n, and this is the number of cycles of alpha minus 2n. This is very similar to the things which we had shown up in the case. Okay, and then of course, I mean there are sub-leading order terms. we are going down in steps of 2. S1 has it for the Gaussian. Okay. The point, of course, is this phi of alpha here. This is independent of them. So the point is, the leading order is given by this here. Good. Okay. So that's what we will meet later. And now maybe let me make a few remarks before we really then go to prove the asymptotic freeness. So maybe first of all, I mean, this formula here, actually, the remark to make is about what I have forgotten here, in that m has to be equal to n. The number of u's and u bars has to be the same, and this is the easy part, to see that it vanishes if they are not the same, because this is just a symmetry condition of our u's. So the first remark, the fact that the star moment in the entries of U, this I mean a moment which contains U and U bars, is 0 if the number of U's and the number of U stars is not the same. This follows quite directly. This follows from the fact that if U is a high unitary, so this U, I can get another high unitary random matrix if I multiply this with a lambda, which is just a complex number of absolute value 1. Also, then also lambda times U is a unitary random matrix for any complex number of absolute value 1. Okay. And this is just invariance, the Haar property of our length. Because I mean, we said the measure on the high unitaries, this Haar measure is invariant, and a multiplication with any unitary, with any element in my group. And of course, I mean a lambda, a complex number of variance 1. I mean, this can be considered as a unitary n times n matrix. The unitary condition for complex numbers, of course, means that I'm on the circle. So this means here I'm multiplying this with an element from my group, and this means the measure which I get under this transportation is the same as before. And this means all the star moment, everything, all the distribution of the entity of this guy is the same as the entity of this guy. Because the measure is invariant under this. Okay, but so this means then that the expectation of the entries in this case, so how are they connected with the entries before? Of course, I multiply a U with a lambda, and a U bar I multiply with a lambda bar. So this means I get m factors lambda, and I get m prime factors lambda bar. So this means this goes over to lambda to the m minus m prime. I get m lambdas, and of course 1 over lambda is lambda bar, so I get m prime lambdas. And this must be the same as the expectation before, because it doesn't change. I mean, the moments of this and the moments of this should be the same, but the moments of this have this extra factor. Okay, but so this means then, and I have this for all lambda, this means if m is not the same as m prime, if m is m prime, then this is just 1, then of course this is no problem, but if m is different from m prime, I have here a complex number which is different from 1, and then of course that this is equal to this means that this has to be 0. It has to be 0. Okay. So this means this has to be the same as the expectation, and if m is not equal to m prime, this can only be if this is equal to 0. Also, I'm not writing the arguments here. So this is 0 if n is different from prime. Okay, so this delta is the easy part of the statement. For this we don't need anything from the symmetry. Okay. But if I have this, then this of course also tells us that such a high unitary matrix, high unitary random matrix, if I consider it in our usual non-commutative probability space where I'm taking the trace, that this is actually what we call a high unitary. So this information is already shows. This shows that if I'm taking the trace and the expectation of a power of my matrix, that this is 0 if this power is not 0. This is 0 for all powers which are integers and not 0. Because if I take, because if I have such a power, if I write this in terms of the entries, it's just given by a product of u's, but there are no u bars. Or if k is negative, it's a product of u bars, but there are no u's. But such guys are all 0. So this is a sum over many things, but they are all 0. Okay. But this here, of course, saying that, so this is our state, in our non-commutative probability space. This, of course, tells us this is the determining condition for our high unitary. So this means that for each n, in n, unitary random matrix is actually a high unitary. So of course, it's the reason that we call a high unitary a high unitary. So I mean, difference. I mean, a high unitary random matrix means I'm specifying all the information about my n times n matrix, which means I give you the joint distribution of all the entries. If I'm looking in my non-commutative probability space, I'm just looking on the expectation of this guy with respect to this. So I'm just calculating those moments. And this is much less information than knowing information about all the entries. Okay, so I mean, a high unitary random matrix refers to this. A high unitary random variable refers to this. A high unitary random matrix refers to the fact that we have the space of unitary matrices equipped with the high measure on it, and this gives us all information about the joint distribution of the entries. Okay, so this tells us, so for each n we have a high unitary element, and of course this means also if n goes to infinity we have a high unitary element. Thus, also going to infinity, our un, un are our unitary random matrices, this converging distribution to a high unitary element u. But of course, this is even true. Each un is a high unitary element for each n. Okay, but this is somewhat analog as saying the Gaussian random matrices converge to a semicircular element. So the high unitary random matrices converge to a high unitary element, but actually it's even stronger. For each n they are already one. In the Gaussian case, of course, it's not true. We only get a semicircular limit. Good. Okay, so with the abstract distribution of our random matrices are very easy. But of course, that's not very exciting. The exciting point will be to see whether we also get asymptotic freeness for that. So the interesting question interesting question, of course, is we also have asymptotic freeness, and actually if I'm talking about U, then I also want to include U star, so I want asymptotic star freeness. Not just looking at moments where I have U, but I'm also including U stars. So I want to see that I have asymptotic star freeness used from deterministic matrices. Okay, and this is indeed the case. That's what we want to prove. But actually, we are only going to prove the most important case where I'm using the U's for rotating deterministic matrices. Oh, okay. So that's the following theorem, which is not the full asymptotic freeness of U's from deterministic matrices, but it's the most important special case of this. Okay, so let me write down the theorem here, which is the main theorem of this section here, and which is one of the main big theorems in free probability theory. Okay, so we take now, let's say, two deterministic sequences of random matrices, each of them converges to something, and then I also take a high unitary random matrix and I conjugate one of them, that is U, and I hope to make them free. So let's say I have two sequences, ANs and BNs, and then, so both of them should be sequences of deterministic n times n matrices. Yeah. Oh, okay. I mean, before the A's usually were the Gaussian random matrices, but now A and B both are deterministic matrices. And of course, we assume that they converge to something in the limit. Yeah? So each of them should have a limit distribution. Let's say AN converges to element A, of course in distribution, and BN converges to element B in some probability space. No? This just means that the moments of AN converge have a limit and the moments of BN have a limit. And this limit we say are the moments of A and the moments of B. Also for A and B in some okay, if I have two such sequences, of course, in general, in the limit, they will not be free. No? I mean, it's okay. So, for example, you can take diagonal matrices for the A's and also for the B's, and of course, they will not be free. No? In the limit. But now we can make them free by also using high unitary random matrices. So, in addition to deterministic matrices, we assume we have a sequence of high unitary random matrices, so those are the UNs, which any n, this should be the sequence of high unitary n times n random matrices. Okay, and then we are saying, now I use the U for conjugating one of the two sequences, let's say the A's, by the U. So this means I'm doing a rotation of the basis of eigenvectors by the U. I mean, the unitary matrix transforms one basis into another. So I'm taking the basis in which the A's are given and transform this by this random U's into some other basis. Good. And so then I'm looking on UN, AN, star. So I'm conjugating the A's by the U's. I don't do anything for the B's. I leave them at the basis where they are, and then I'm claiming that this converges now in distribution infinity to the pair A comma B, where of course the A is the limit of the A's, and the B is the limit of the B's, but now in addition the A and B are really free. So there So in particular, this means that the sequence of UN A and UN star and the sequence Pn, they are asymptotically free. So in particular, the two sequences here, so the UN, AN, UN star, and the Bn, free if the size, asymptotically means if the size n goes to infinity. Okay, and of course you should note, and that's what I already said before, that if I'm conjugating the an by the un, I'm not changing the distribution of this sequence. Because I mean, if I'm taking traces, I don't see the effect of the u. Also, this means the an converges to a, but the UN, A and UN star also converges to A in distribution. Because this is not changed. But what is changed is somehow the relation, the limit between those two sequences. So now in the limit, the A and the B are really becoming free. I mean here, of course I could realize that the A and B may be somewhere, but of course they are not free. There might be a joint distribution here between A and B at the limit, but this is arbitrary because it depends how we realize things. Okay. But this tells us it doesn't matter how we realize the relation between A and B in the beginning. If you do this random rotation of the eigenvalue basis of the AN, then really things are getting free. Good. Okay, so that's what we have to prove. And so let's prove it. Of course, we need this information here about the Weingarten function. And the idea is, of course, the same as in the Gaussian case. We just write down the joint moments alternatingly in, let's say, powers of this and powers of this. And we hope that we get a formula that we can really calculate this sufficiently good enough such that we can control the limit if n goes to infinity, and we get a formula from which we see that things in the limit are free. So what we want to calculate are mixed moments. I mean, in those two. I mean, that those are two sequences we are interested. So we have to look on them on all their joint moments actually. I mean, all the joint moments are some products of those guys, a product of those guys in any order. And this means, of course, what we have will be a power of the first guy times the power of the second guy times another power of the first guy times some power of the second guy and so on. Okay, so we're looking on powers of those guys. So calculate moments of the form. Okay, now moments are, of course, with respect to taking the trace and the expectation. The expectation, of course, is over the unitary matrices. This deterministic matrix has no random matrix, no randomness. So for them, I only apply the trace, but the E applies to U's. Okay, and then I take here, let's say, the power of the first guy, and of course the power of UA U star is just the U of the power of this one. Because I also have to trace. Okay, so I take UN AN, let's say to some power, UN star. So this is the same as taking the Q1 power of UN AN UN star. Because the UN star in the middle just go away because the UNs are unitaries. Then I multiply this by the power of the second sequence of the B's, power U1. Then I multiply again with the power of the first, so it's again the UN AN Q2 UN star with the BN Q2 and so on. And let's say I multiply M of them. So I analyze this UN AN QM star and multiply this Bn to the power Pn. Okay, so that's the guys which I have to consider for all possible choices of the powers which I have here. And of course also the M, how many I multiply. So this for all choices of M and Q1 up to Qn P1 up to Pm. And I mean they can be in N, or maybe I can also allow in 0 in particular because in between it doesn't really make a big difference. But at the beginning or the end, I mean it's the question whether I start with an A or with a B, or whether I start with an A and a B. So maybe we can also allow that some of the powers are 0. Good, okay, so we have to calculate this. And then of course consider in the end, after we hopefully get a nice formula which we can control, and consider then the limit to infinity. Good. And of course we do this calculation in terms of the entries of our matrices, so again we should give names to the entries. Of course we use the Uij. But here, of course, I only need the power of A. So this means I just give a specific name to this. So the power, let's say the power K of A, I denote those energies by Aij, and I put in as K. From 1 to N, and the same for the B, the K power of B, I just call Bij, and I put in some EXK. And as before, in all our calculations, this shift in the permutation group, which shifts everything by 1, will at some point come into the game, and as usual we call this gamma. Gamma is this cycle which shifts 1 to 2, 2 to 3, and so on, up to -1, which goes to M, and then I'm going back to 1. So this is a long cycle in the permutation. Good. Okay, now we have to look for this thing. So let me call it star and then start our calculation. So what is this? Good. Okay, so of course, if I'm taking the trace of products, I'm multiplying all the entries and I have a lot of indices over which I have to sum. And the trace, here's the normalized trace, so I will get a factor 1 over n. 1 over n for this. So first I have the 1 over n. Okay, and then I have to sum over all the indices which are showing up. And now I'm grouping the indices into some classes. So some of them I call them I prime, J, and J prime. Hopefully it's clear why I do this, at least after a while. So I'm summing over indices, some of them I call I, some of them I prime, some J, and some J prime. And of each of them I have m many, and all of them can take all values between Good. Okay, and then I take the expectation of, and now I take the trace of this big product. So what is this product? So the first guy is U. So there I have the U, and there I call the index I1 J1. This is period. Then I multiply this with the AN to the Q1. So this is now the A. Okay, the index here must of course be the same as this. This is the J1. Then the next index I can call it as I like, and I like to call it J prime. But for this J prime, of course this is the A from the A's first. Good. So this is now getting multiplied with the U star. And of course the entry of U star is to U bar, where the indices are also transposed. So this means I get here U bar. And this index here, so this is now the first index of the U star, but actually here this is the second index. So this is here the J prime of 1. And then I have here another index, which I call now I prime. I prime of 1. Good. And now it's getting multiplied with the, now I'm up to here. Now I multiply with the B. So again, the B's are called little B's. That's here position 1. Then the first entry here must be this one. So this is I prime of 1. And so I can now give a name to this. And now actually, you see now I will continue again here. And now of course I come back to this notation. So I have now the IQ here. And then of course I continue again in the same way as here. Yeah. Okay. Up to the end. Of course, what I'm doing at the end, I will get here. So the last term, of course, is just the same thing here. Where, of course, I mean the structure of the indices is the same. Only the one is the M. So I have the U I M J M the A J M J prime M bar I prime, okay, I prime M J prime M B I prime M, and of course here I have the I, and now of course I would have the M plus 1, but of course this means I'm going back in a certain way, which of course I have to do because I have to trace. So the last index must be the same as the first one, so here I have okay, so this is just, I mean, all this is just matrix multiplication and taking the trace. Taking the trace means I'm summing over the I1. And you see I have distributed the names of the indices such that the U's are just going with the I into J, and the U bars are going with the I prime into J prime. Exactly as I denoted in this big formula. Yeah, okay, and now, of course I can separate, of course I mean the U's, everything here commutes, so I can separate the U's from the A's and the B's. So I have three classes of guys, I mean I have the U and the U bars, and I have the A's and I have the B's. So let me write them separately, 1 over n, and I still have here the sum over all these I prime, J and J prime indices, and let me first take all the A's. So what is the structure of the A's? For the A's, I have, yeah, you see the A's have the indices J and J prime. Also I have here J1, J prime 1 at position 1. This is multiplied up to A of Jm, J prime, position n. I mean I have chosen the indices such that they are nice for the U and the U bar. And then of course for the A's and the B's they are just, this is determined by this. So for the A's they are also nice, they are J and J prime at the same position. For the B's, you see I have the I prime and the I. That's also, the J's are going to the A's and the I's are going to the B's. So I have here B, I have I prime of 1, I of 2. But you see here I have a shift. No? It's not the same as before, but this is of course the effect of gamma. No? Gamma is shifted. And I have here the nth version of I prime M and I omega. Okay, and then of course I have the contribution of my use. For the use, I'm acting with my expectation. So I have now here also the expectation of the use, and for the use, you see I have exactly how it was in this weak form. So I have the U1, J1 up to UIM, JM, so this up to this, and then multiplied with the corresponding U bar. So I have the U bar I prime of 1, J prime of 1 up to U bar I prime of M, J prime of M. Good. And now, of course, we have to express this somehow, and it's exactly our Wick formula which tells us how to do this. So here was our Wick formula which says that this can be written in terms of the Weingarten function. And of course, M is here automatically equal to M prime, because I'm using here a situation where I have the same number of U and U stars. So this delta condition is satisfied, and so what I get from here, this here is the summation. This gives me this gives me a couple of delta functions, exactly the delta function as I have here. So this is delta of, I'm summing over alpha and beta in Sm, and for each alpha and beta I get a contribution of delta functions which tells me that delta, that I of beta 1 must be the same as I prime of 1, that I of beta m must be the same as I prime of m, which means the I prime, so I put to some i's, and the same for the j, so the j of alpha 1 must be the same as j prime of 1 up to the j of alpha m must be the same as the j prime of m, and then I get a factor. If all those delta conditions are satisfied, then I get something which is not 0, and this is this Weingarten function. I get W of n alpha beta. Good. Okay, and this is now quite good. You see this fits. So now of course we do the usual business. We exchange the summations over the indices and the summations over this alpha and beta. And then I'm summing over alpha and beta. And then, for fixed alpha and beta, this delta condition tells me exactly that the I indices and the I prime indices are connected. So if I'm choosing, let's say, an I prime index, then all the I indices are exactly determined. If I'm choosing a J prime index, then all the J indices are determined. So these delta factors just tell me that in the sum over I prime, J prime, I mean the I is determined in terms of the I prime, and J is determined in terms of the J prime, so I'm just summing over I prime and J prime. Or, let's say over I prime and J. Can eliminate, I mean of this pair I can eliminate one in terms of the other, and for this pair I can also do it. So let me write this down here. So here we are. Okay, so I'm writing, so we are here, I'm writing this again. I'm now exchanging the summation over the i's, all the indices and the alpha and beta. So what do I have? So I have, okay, first this one on my own. Then I have now a sum over alpha and beta over Sm. If I'm fixing this, I have here the Weingarten function. This only depends on alpha and beta. So I can put this here. The Weingarten function of n alpha minus 1 beta. And then I have the sum. Here I have the sum over I prime, j prime, but because those delta functions tell me that I can eliminate 2 of the 4. So actually in the end I only left with summing over, let's say, I prime and j. I still have. For each of them I have m variables and indices that they can run from 1 to n. Good, and so what is the contribution which is left? This here is now gone. This is replaced by the Weingarten function and all the delta functions which we have taken into account, but of course now we have to replace. I mean, here we still have all the j primes, I and I primes, and we have now to make the replacement. So what do we have? Let's see, so I have here the A goes with the j1, so the j I'm keeping. But then the next one is the j prime, and the j prime, this I replace by the j. Because this delta condition tells me that the j prime has to be the same as a j at this alpha position. So this j prime of 1, I'm replacing by j alpha of 1. And so on. I have here A up to jm, j of alpha. Good. Okay, for the b's, same for the b's. The b's are going with the I prime and the I, and I'm keeping the I prime, so this means I'm replacing the I. So you see I'm keeping the first of the indices. Okay, I'm replacing the second in terms of the other. Okay. So I have here I prime of 1, and then this I of 2, this is now replaced by I prime. Okay, now of course we have to go backwards with the beta. So what I have here is actually I prime of beta to minus 1, and I have to take gamma of 1. Because I have here the 2, this is the gamma of 1, and this here tells me how to replace the I prime by the I, but I want to do the other way around, so this means I have to move the beta as beta to the minus 1 to this side. This goes up to b I prime m and I prime beta minus 1 of n. Yeah, but now we see that what we have here is something which we also had before in the Gaussian case. So the summation over the j is only showing up here. J indices are now only showing up at the a's. And what I'm doing here is I'm summing, I have here the j's, j1 up to jm, and here I have also the j's, but now perturbed with this alpha condition. But summing over those guys was actually a product of traces. Traces according to the cycle structure of alpha. So if I'm doing the sum over those guys, and there I'm just summing over the j's, then this gives me the trace of alpha of the corresponding quantities, which is Q1 up to K of Qn. So this notation was I'm taking a product of traces, and a pitch product for each cycle of alpha. I take a trace, and I'm taking the elements which sit at the positions of this cycle. I'm taking the elements out from here because those are the A matrices which I have here, which I consider. So I have here this, here I have the index 1, here I have the index m. Good. And if I do the same for the B's, I'm summing over the I primes. I do the same. The first indices are just in the natural order, and the other ones are permuted by beta to the minus 1 gamma. So I get for the summation over this, I'm summing this over I prime, I get the same in the trace, but now according to the cycle decomposition of beta to the minus 1 gamma of the matrices which are sitting at those positions, and those are the B. first position I have the power P1 of B, at the last position I have the power PM. Because I mean, those guys are the entries of those matrices. And so you see now again we have the quite satisfying behavior that actually this very wide sum can be expressed in terms just of moments of our matrices A and B. The sum over all these entries in a very complicated form actually really sums up to some products of traces, to matrices. And this is really our distribution. And of course, there will survive something. Okay, but now, of course, again, this is for finite n, so we have n dependence, which we should maybe also make explicit. So what I have here, let me write it again, is the sum over alpha, beta, equals m. Then I have the Weingarten function, n alpha minus 1 beta. And now, of course, what converges is, of course, not the unnormalized trace, but a normalized trace. So we have to go over a little tr, which is a normalized trace. And I mean, the difference between them is a factor of 1 over n, or to do another, I mean, this trace is n times the little trace, and here this trace is a product of so many factors as I have cycles of this guy. So the difference between this is the number of cycles, n times n to the power number of cycles of this. So what I get here is the number of cycles of this term, alpha, plus the number of cycles of this guy, beta minus 1, gamma, and then I have this 1 over n from here, so I have here minus 1. Yeah, so you see now we are very close to things we did at the Gaussian case, but of course now we also have to take into account that this also has a dependency on n. And we should see what is the leading order. And of course, hopefully, the leading order is n to the 0. No? I mean, things should not explode. If we have n to some positive power, things will explode. Okay, and this means we have done a wrong normalization. If the leading order is n to a negative power, then everything will go to 0. This means also our normalization was not good. So, of course, I have given you the right normalization, so this means the leading order here should be n to the 0. We have to see this. Good, so I can take this away. The leading order of the Weingarten function is here. So this here, which I told you. So we know the Weingarten function of n, and here we have now as a permutation, we have alpha to the minus 1 times beta. That this, okay, this has the leading order has some coefficient, which we don't care about what this is. But it goes with n to the number of cycles of this alpha to the minus 1 minus 2n. That's exactly the same. So the alpha here is now the alpha to the minus 1 beta. Okay, and then of course some terms of smaller order, but they disappear in the limit compared to this one. Good. So this means the leading order in this contribution is thus given by this term here and the leading order of this. Hence, the leading order in, let's say, star, or this star, this equation, this is n to the contribution coming from the Weingarten function, which is the number of cycles of alpha to the minus 1 beta, and then we have the other terms plus of cycles of alpha plus number of cycles of equal to minus 1 gamma minus 2m minus 1. Okay, and now of course we have to see that this guy here is always less or equal to 0. No? The best it can be is equal to 0, and of course the terms where it is equal to 0 are the ones which survive in the middle. Good. Okay, this is not totally trivial, and maybe I give you some information about how to see this, and maybe in the assignments we will do a little bit more in this direction. Also, we can do like this. Okay, so first of all, I mean, what is behind this is essentially a triangle inequality. So you see we are multiplying things here, and we have here the function of it. And this is a kind of triangle inequality, but this should be better formulated not in the number of cycles, but in the quantity which we calculate from this. So namely, if you write for alpha in this, I denote, let's say, the absolute value of alpha, I define this by m minus the number of cycles. So I mean, this is our usual number of cycles. And now I take m minus the number of cycles, and then this guy has actually a very nice meaning also in group theoretic language, and it satisfies the triangle inequality. Okay, so then it is easy, maybe relatively easy, no? So it's not totally trivial, but it's a little bit, but it can be done on elementary level. So then it is easy to see. So first is that I can also give another description of this quantity here. So namely, this absolute value of alpha is actually the minimal non-negative integer k. In particular, it's not greater than equal to 0. It might not be so clear for this directly. So it's an integer k such that alpha can be written as a product of k transpositions. So I mean, any permutation can be written as a product of transpositions. But I take now, I mean, there are many ways of doing this, but I'm now taking such a representation where I take the minimal number of transpositions. Okay, such that alpha can be written as a product of k transpositions. Yeah? And the transposition, of course, that's a special permutation which only exchanges two numbers. So this means that it has a cycle of length 2, and the other ones are just fixed point. Transposition is just exchanging an I with a j for I different from j. Okay. And any permutation can be written as a product of such things. Okay. And I take here the minimal representation, and if alpha is the identity element, okay, then I don't need any transposition. Then this alpha is equal to 0. Otherwise, it will be 1 or bigger. Good. Okay. And the second thing, which is relevant for us here, is that actually this guy satisfies a triangle inequality. So it really makes sense to denote it like an absolute value. So this satisfies the triangle inequality, which is quite easy to see if you have this interpretation in terms of writing in terms of transpositions. So namely, if I'm multiplying two permutations, then the absolute value of them is less than the absolute value of alpha plus 1. So it's more or less clear with this definition for all alpha and beta permutations. Okay, now let us see what the quantity which we have here is in terms of this absolute value. what we want to see is that this power of n is less or equal to 0. Of course, we will see this by the triangle. Because maybe you already see that the terms which we have there, if you multiply all of them together, we get something nice and simple. Good, so we should note that this term, which we have in the exponent of n, so which is this one, so we have n to the exponent is the number of alpha minus 1 beta plus the number of cycles of alpha plus the number of cycles of beta minus 1 gamma minus 2m minus 1. So let me first rewrite this in terms of this absolute value. So I mean, the difference is just that I should, so this absolute value of alpha, this is m minus the absolute value. So this means for each transition, I'm adding an m, so I'm adding 3 m's, this is minus 2m, I get m, I have the minus 1 here, and then I'm replacing this by the negative of the absolute value. So I have here minus the absolute value of alpha minus 1 beta minus the absolute value of alpha minus the absolute value of beta to minus 1 gamma. Okay. This actually now is less or equal to 0 because, why? Because this guy here is greater than this one. So since alpha minus 1 beta plus alpha plus beta to the minus 1 gamma, the absolute value of this, the triangle inequality, is bigger than if I multiply all the arguments together. So this is greater than, I multiply alpha with alpha to the minus 1 beta with beta to the minus 1 gamma. So the triangle inequality tells me the absolute value of the product of those three guys is less than the sum of the absolute values, which is here. Okay, but this product of course is now simple because alpha minus 1 goes away, beta minus 1 goes away. So I'm left with the absolute value of gamma. But what is this? I mean, this is m minus the number of cycles of gamma, but gamma has only one cycle, right? It's one long cycle. So this is m minus 1. And so you see this is bigger than this. So if I take m minus 1 minus this, I get something which is at most 0. Okay, so this tells us that actually in our limit formula, which I have now erased, so I try to avoid. So okay, anyhow, so we had this formula where we had written the mixed moment for n in terms of n to this power, and then we had the contribution, the traces of the a's and the traces of the b's. Okay, now this guy here, if n goes to infinity, goes to 0 unless I really have equality here. Okay, which means also equality here. Okay, so what we get from this is when I'm looking on the limit n going to infinity of our trace of the product, our moment, this was the un, an, q1, un star, and so on, up to en to the qm. This was our, we had the formula for this for time n, and the limit sum over alpha and beta. But now only we have alpha and betas where we have equality here. And this really is equal to 0. Or maybe in this form, so this really tells us that the sum of alpha to the minus 1 beta plus alpha plus beta to the minus 1 gamma has to be equal to minus 1. That's unpaired, that unpairs alpha and beta, which really make a contribution in the limit. Because then this contribution here is exactly equal to 0. Of course, it's not so clear maybe what this means at the moment, but at least we have a precise formula. And then we get the contribution of the moments of the A's and the moments of the B's. And this was given in terms of the traces according to the cycle of alpha, which of course the limit here converges to phi alpha of the limiting moment of the A's, which are the A to the Q1 to the A to the Qm, times the product of the corresponding moment of the B's and the B's. Then we had beta to the minus 1 gamma as the index. This product of the phi's according to the cycles of beta to the minus 1 gamma of the moments of the B to the P1 to the Pn. Good. Okay, so you see we get a formula for these mixed moments in our rotated A's and the B's, somehow in terms of the limit distribution of the A's and the B's. Okay, now in the Gaussian case, we just said, okay, we know this formula. This is the same as the formula which we know for free variables. And this here is at the moment not so clear. So I mean, in principle we know if the A's and the B's are free that we have a formula which should involve non-crossing partitions. But this here is a permutation group, and this condition here looks a bit strange. So it's from this, it's not directly clear that this is really a formula which we know for free variables. Of course, it has to be, and there will be some correspondence, but for this, I mean, one really would have to understand this better, and I'm not going to do this, but actually I'm just using this formula to show that we have asymptotic freeness. I mean, of course, we can also show asymptotic freeness by the definition of freeness. So we have to see that under some special conditions, alternating moments must be 0. Okay, and for this, of course, we should have this formula not only for a product of powers of our variables, but we should have it for polynomials. Because the definition of freeness means we should take elements in the algebra generated by our variables, which means we should look on moments or on polynomials, and then we should look on centered polynomials. But this formula here is linear in the A's and the B's and those guys, so actually we can extend this by multilinearity to polynomials. So we have the same formula also for polynomials in A's and polynomials in B's. And then from this we can just show, just by a definition of freeness, that we get here is really a formula for describing free variables. Okay, so by multilinearity in the arguments which I have here, this formula goes over to the situation I consider polynomials. This goes over to polynomials. Let's say I take polynomials fi in the A's and gi's in the B's, and then this tells me that I'm taking the limit over infinity, trace as an expectation. Now I'm taking u, now I take here f1 of an. So this is now a polynomial, not just a power, but monomial in un. And of course you should see that, of course, if I take f1 of u, a, n, u star, this is the same as u, f1 of a, n, u, n star. Because I mean, the F1 is just a linear combination of powers. So. Okay, then I take here a polynomial B, and so on. Up to the end, I have another polynomial in N star, and the last polynomial Gm in these. Okay, index matrices are just n's, or the matrices. And this limit is then the same as this, so I'm summing over all alpha and beta in the permutation group, where I have to satisfy this kind of triangle equality, alpha to the minus 1 beta plus the absolute value of alpha plus the absolute value of to the minus 1 gamma has to be equal to the minus 1. And then I have here phi alpha of now the corresponding variable which I have here, which is f1 of a, comma fn. So the distribution of an converges to a, which means of course that the distribution of f1 of an converges to f1 of a, and so on. Okay, here I have phi of beta to the minus 1 gamma, and here I have g1 of b, comma gn. So this is just again, this is a product of moments of those variables here. Good. Okay, maybe what I had forgotten before actually, there's one term missing, because we also had the Weingarten function, we left the tracing limit, because the leading coefficient is not necessarily 1, but it was something which we call phi. Also, this was phi of alpha minus 1. And of course, we also have this here. Good. Okay, so now what we want to see is a definition of freeness. So this means I should now see that this here is a formula for describing mixed moments. So this really, I mean this of course is the corresponding joint limit here. So this is phi of f1 of a, g1 of b to fm of a, gm of b. Okay, so we have to see that this being equal to this really describes free variables. Also, we have to see that if I have A and B, for which the mixed moments are given by this, that this means they are free. So I have to, for the definition of freeness, I have to check, actually I have to look on alternating moments, but where each of them is centered, so phi of this is 0, phi of this is 0, phi of this is 0, I have to see that this is equal to 0. So this formula, that this is equal to this, should tell me that in this case this is equal to 0. So that's what I have to see from this formula. I don't really have to understand really the structure of this formula, I just have to see that in this special case it gives me 0. And of course it's a sum over many terms, so what I really have to see is that hopefully each term here gives me 0. we have to show that then also this guy is equal to 0. We have to show that phi of f1 of A, g1 of B up to fm of A, gm of B is equal to 0. Where we know that the f is given by this formula. Good, okay. And so, yeah. How can we see that this is equal to 0? I mean, those guys here are products of moments according to the cycles. Okay. What we know is that such a product such a guy is equal to 0. Okay, so we should, if we have a term here, either here or here, then we just apply phi to one of those guys, then this is 0. Okay. And I mean, one of these guys, this means in this product, that this or this should have a fixed point. Because then we have one product for this cycle which is this fixed point, and this is just the phi of one of those guys. I mean, if the cycles are longer, then we are multiplying some of them and taking the phi. Okay, so the question is again about fixed points. Whether we have at least a fixed point here or a fixed point here. But this is given if we have this condition here. So, namely, if we have alpha to the minus 1 beta plus alpha plus beta to the minus 1 gamma is equal to m minus 1, and that's only alpha and beta we are considering, then I'm claiming then at least one of the two alpha or beta minus 1 gamma must have a fixed point. Then at least one of alpha in Sm or beta minus 1 gamma in Sm must have a fixed point. Okay, why this? If I'm assuming okay, so what does this condition here tell me? This is at least m minus 1, so this is equal to m minus 1, which means of course that this and this cannot be too big. So I mean, it cannot be that both of them are greater or equal than m minus 1 over 2. Assumption which I have on my pair alpha and beta, so this assumption this implies that alpha must be less or equal to m minus 2 over 2, or beta must be equal beta minus 1 gamma must be less or equal to m minus 1 over 2. Because if both of them would be strictly greater than this, then the sum of them is also greater. Then the sum is greater than n minus 1. And here we say the sum of them plus something which is also positive is n minus 1. So I mean, it cannot be that this and this both are strictly greater than n minus 1 over 2. So at least one of them must satisfy this here. Good. But if I have this here, then, so I have here, let's say, a permutation for which the absolute value is less than n minus 2 over 2. But we have seen the absolute value is, well, I have told you, the absolute value is the minimal number of factors which I have to use of transpositions for writing this. So this means this here, that alpha can be written as a product of less than m minus 2, m minus 1 over 2 transpositions. Well, I have this means, because this has the meaning that it's given by the minimal number of factors, I need to write it as a
transpositions, so this means it can be written as less than so many transpositions, but now a transposition is only moving 2 elements. Oh, okay. So if I have a product of less than m minus 1 over 2 transposition, this product can only move m minus 2 elements. Because each of them involves only m minus 2 elements, so the maximum thing I can move if I multiply so many of them is m minus 1. But I have a permutation of m elements, so this means at least one element is not moved, which is a fixed point. So I can move most m minus 1 elements. Of course, if I multiply 2 transpositions, they can also move less. No? I mean, 2 transpositions can move 4 elements, but of course if I multiply a transposition with itself, it doesn't move anything. Or if I move a transposition is another one which has overlap, there will also be only 3 elements involved. Okay, but the worst case which can happen is I'm moving the number of transpositions times 2, many elements, and this in this case is at most m minus 1. But this means there must be at least one element which is not moved, and this means I have at least one fixed point. Good, but this means for all the situations over which I sum here, over all the pairs alpha and beta, it always happens that at least one of them, of those guys, alpha and beta to the minus 1 gamma, is a fixed point. Maybe not both of them, but at least one of them. Yeah, okay, but then the corresponding term in the sum will be equal to 0. No? Because if alpha is a fixed point, then this here is a product of things, and one of the factors is just phi applied to one of the guys at the position of the fixed point. And by our assumption, this is 0. Okay, if this guy has a fixed point, then the same will happen here. So then a bit more space for the last conclusion. And then we are done for today. Okay, so we are now in the situation that we have a fixed point, at least for alpha or for beta to the minus 1 gamma, and then these corresponding factors must be 0. So one of this phi alpha or phi of beta minus 1 gamma. Okay, but then of course we are summing here over many pairs alpha and beta, but for each of them we know that one of those terms is 0, so the contribution is 0, which means we are summing over many zeros, not the whole sum is just 0. Each term in this formula okay, this proves it. Good. Okay, so you see, the calculation for the asymptotic freeness of the high unitaries is a bit more complicated than for the Gaussian case, but in principle it goes in the same way. But we have to involve the Weingarten function, which is more complicated, and here in the final calculation we get something which is not directly clear that this is the formula which we know for free variables. Oh? Okay, but it must be, of course, correlated, and maybe next time I write down how we would write this formula in our language of non-crossing partitions. And then, of course, there should be a correspondence between those two formulas, and this tells us somehow that we can embed non-crossing partitions in the permutation group. We already did this before. In the Gaussian case, the pairing, we also considered as something in the permutation group, and we could characterize there the non-crossing guys, the ones which survive the limit, the non-crossing ones, but this was a condition in the permutation group. And here we have a more general, not just for pairing, But for all non-crossing partitions, somehow there's a correspondence. Or the non-crossing partitions are somehow embedded in the permutation group. And so, I mean, this gives you the idea how this should work. And the assignments, the new assignments, which hopefully come out today, I mean, they ask you to look at least at some examples on these correspondence, so that you get some idea about this. Good, okay, so that's